Hello, everyone, and welcome to the ninth topic in the SS3 First Term Physics curriculum. Now, this is week 9, the final topic we'll be looking at in the SS3 First Term Physics curriculum. And as I mentioned in the last video, it's actually a continuation of what we started in week 8, where we started looking at the electromagnetic field in the aspect of their applications, such as electric motors, such as the moving coil galvanometer and the likes like that. Okay, now in this particular one, we'll be focusing on electromagnetic induction, which is one of the work of Michael Faraday. It has interesting applications, and there are several devices around us that work solely on the applications of the electromagnetic induction. So which is why under this topic, we're going to start by looking at the concept of electromagnetic induction, where we'll first define what electromagnetic induction truly is. Then after that, we look at what happens to the induced EMF in a straight conductor. And we're going to explain that by using a concept known as the Fleming's right-hand rule. It's quite different from the left-hand rule, but you still do not have to forget what the left-hand rule says. Remember that in the left-hand rule, what you are looking at is the direction of force when you have a straight conductor in a magnetic field. But in this case, we'll be looking at what happens to the EMF that is induced in a conductor when you have electromagnetic induction. So that is by the Fleming's right-hand rule. Now, after that, we then go into the laws of electromagnetic induction. At this point, it gets really interesting. There are two laws we're going to study at that point. We look at the Michael Faraday's law of electromagnetic induction, and then we look at another law that is known as the Lenz's law of electromagnetic induction. We're going to state the law, we'll give the mathematical explanation of that, and then we apply them to answer questions on electromagnetic induction. After that, we then go to a study of a particular type of current known as the Eddy current, which is something that will pop up a lot when we talk about electromagnetic induction, especially as touching the areas of the application of the laws of electromagnetic induction. There are some things we have to look at there, such as eddy current, hysteresis laws, and other things like that. So we'll start by looking at what does eddy current mean and how does it affect electromagnetic induction. After that, we then look at electrical devices that use the principle of electromagnetic induction. We're talking about the DC generator, the AC generator, transformer, and other devices that apply the principles of electromagnetic induction. And then to close the topic, we'll then look at several other questions or problems on electromagnetic induction from different exams, the WAEC exams, the JAMB exams, the NECO exams, and so on. And don't forget that we'll always give you tips as to how you can solve those kind of questions without error. This is why you can't afford to miss any part of this lesson. So if you're yet to be subscribed to the channel, kindly click the subscribe button and also hit the notification bell icon so that you don't miss any of the amazing content that we produce right here on Oya Learn, your flawless school too. And don't forget to help us to reach many more students like you who need the kind of content that we produce right here on our channel by clicking the share button. That way they too can interact with the amazing content right here on Oya Learn and also improve on their academic life. Do not forget that if you do have any question as to what we are learning in the topic itself, or perhaps if there's something you found during your own study time that you'd like some help with, remember that we are always here for you. All you need to do is put a question across to us by dropping it in the comment section of any of our videos. And we promise to attend to all of your questions. So let me say thank you to you for already subscribing to the channel and for interacting with the videos that we make right here on Oya Learn. And if you're ready, let us go into electromagnetic induction by looking at what the concepts really mean. Let's define first, what does electromagnetic induction mean? In 1831, Michael Faraday conducted an experiment involving coils that are wound round a steel ring, and then he observed how there's a deflection in the galvanometer when you put on the switch and then switch off the circuit. Now, this led to what formed the foundation of what we know today as electromagnetic induction. However, in today's laboratory, if you're going to observe the same thing that Michael Faraday did, you need this experiment to be in this particular form, where you have a solenoid, that is a coil of a conductor around a soft iron coil, right? You have a cylinder with a soft iron coil embedded within, and then you have a coil around it such that the coil is tightly wound together. Now, when you connect the end of this solenoid to a galvanometer, and then you take a magnet, say a bar magnet for example, and then you begin to move it relatively with that coil, you begin to see deflections in the galvanometer that is connected to the solenoid. Now, here's what you need to do. At first, you can start by keeping the magnet itself stationary, and then you move the coil either to the magnet and then later from the magnet. And always take note of the deflections you see in the galvanometer. That is, when you are moving it towards the magnet, look at the deflection in the galvanometer, take note of that, then move it away from the magnet and see the deflection you also observe and take note of that as well. Now, after you've done that, this time you now keep the coil itself stationary and then move the magnet to the coil and note the deflection that you're going to see in the galvanometer, and then you move the magnet away from the coil and also observe the deflection in the galvanometer. Then you can then begin to move them relatively to each other and observe what happens at the deflections you see in the galvanometer. Now, what you're going to see from this is that every time you make motion, either you keep the coil stationary or the magnet stationary, as long as there is motion in that system, there is always going to be induced current or induced EMF. Okay? And that is what we know today as electromagnetic induction. The foundation of this started with the experiment from Michael Faraday. And here are the three conclusions you're going to get from that experiment. You see here, the first thing you will note is that there is always current induced in the conductor when it moves relatively with a magnetic field. Because as you are moving the magnet or you are moving the coil, you are observing deflection in the galvanometer, showing that current is induced. Now, the second conclusion from that experiment is that the amount of current induced depends on, first, if you are moving them very fast, you will see that there's going to be more current induced. When you move it slowly, then less current is induced. So it depends on the speed of the motion. Secondly, it depends on the number of turns in the coil. So if your solenoid has more coils in it, then no matter how the motion is, you will get more current as compared to the solenoid that has less turns. Okay? And then finally, the presence of that soft iron core in that solenoid can also affect the induced current or induced EMF. And then the third and final conclusion from that experiment is that the direction of the current will always reverse every time you change the direction of the motion. That is, if I move the magnet now towards the coil and I observe the deflection, by the time I'm moving it away, it will be in the opposite direction that the galvanometer will deflect towards, telling you that the direction of current is always reversed when the direction of motion producing the current is reversed. Now, these are the conclusions from the experiment to prove electromagnetic induction. So from this now we can then go on to define what electromagnetic induction actually means. So if you are asked, perhaps in class or in an exam, to define electromagnetic induction, this is how you can define it. Electromagnetic induction is the production of current or EMF in a conductor when it moves relatively with a magnetic field or magnet. So that is, whenever you are moving a conductor relatively with a magnet or magnetic field, and then you produce electric current or electric potential difference known as EMF, then that phenomenon is what is called electromagnetic induction. And that's how we define electromagnetic induction. When you have a straight conductor and then that conductor moves in a uniform magnetic field, there is always an induced EMF, right? And the direction of that induced EMF can be determined by applying what is known as the Fleming's right hand rule. Now, what I'm saying is this, is that there's always induced EMF when a straight conductor moves relative to the line of force of a uniform magnetic field. Okay, now that induced EMF, to get the direction, we apply the Fleming's right hand rule, and this is what the Fleming's right hand rule states. So it says that when you hold the thumb, the forefinger, and the middle finger of your right hand relatively at 90 degrees to each other. Now, let me mention this. What you are seeing on your screen here is actually an inverse image. It's a flipped image of what is actually happening here. So when I raise my right hand here, what I'm waving at you right now is my right hand. But because of the way this video is produced, you are seeing a flipped image, which means you may see it as my left hand. But note that this is actually my right hand. Okay, so I can actually demonstrate it by using my left hand, which will look more like a right hand to you. But hold out your own right hand so that you understand the concept. So whether you are looking at it from the flipped image perspective, or if you truly understand the physics behind flipped images and can actually change it in your own mind, well, it will work for you. But the best way to understand this concept is you personally doing exactly what I say right now. Okay, hold up your right hand. Now, you see the way I'm doing this now? Make sure your thumb is pointing upwards, your forefinger is pointing forward, and then your middle finger is pointing towards your own left. Okay, look at it now. You see they are held at 90 degrees to each other. Now what you see here is this. If this were the same thing as what happens when you move a straight conductor through a uniform magnetic field, what you're going to observe is this, is that if your forefinger here is pointing in the direction of the magnetic field and your thumb is pointing in the direction of the motion of the conductor relative to the magnetic field, then your middle finger points to the direction of the induced EMF or induced current. Do you get it now? Let's put it down in writing. If the thumb, forefinger, or if you like, you can call it the index finger, and middle finger of the right hand are held mutually at 90 degrees to each other, such that the forefinger points in the direction of the magnetic field while the thumb points in the direction of motion of the straight conductor. In which EMF is induced. Then the middle finger points in the direction of the induced EMF or current. Now, this is how you can tell the direction of the induced current or EMF whenever you move a straight conductor relative to a magnetic field of equal strength. When you have two magnetic fields of equal strength and then you move a conductor relative to it, this is how you get the direction of the induced current or EMF. Now, there are some things you still have to maintain even when you do this experiment. Don't forget that the faster the motion of the conductor itself, the more the current that will be induced in it, or the more the EMF induced in that conductor. And also don't forget that induced current or induced EMF is at maximum when the conductor is moving perpendicularly to the field. So when they are 90 degrees to each other, you're going to get the maximum induced current and maximum induced EMF. And then you get 0 when it is moving parallel to the magnetic field. But don't forget, if you hold your right hand, if you hold the thumb, the forefinger and the middle finger at 90 degrees to each other, the thumb shows the direction of the motion, the forefinger shows the direction of the magnetic field, while the middle finger shows the direction of the induced EMF or induced current. Now that you understand the direction of the motion, the direction of the magnetic field, and the direction of induced EMF or induced current using the Fleming's right-hand rule, let me show you how you can measure, calculate the induced EMF in a straight conductor. So let's say, for example, you're asked to calculate the induced EMF in a straight conductor of 50 centimeters length moving parallel to a magnetic field of strength 0.2 Tesla. Now, we have the length, we have the strength of the magnetic field. One more thing required here is the speed at a speed of 2 meters per second. Now, how do you calculate the induced EMF given these parameters? Now, note that the induced EMF is given by a product of the magnetic flux density, the length, and velocity of the conductor. So when we are solving a problem like this, here's what you do. You say the induced EMF equals, now we have the magnetic flux density, which is 0.2. Now you're going to multiply this by the length. The length of the conductor is 50 centimeters, which you have to convert into meters, and that will give you 0.5. Now we multiply this by the velocity, which is 2 meters per second. Now when you calculate this, what do you get? 0.5 times 2 will give you 1. 1 times 0.2 and you have 0.2. Okay, this is measured in volts, and this is how you calculate the EMF induced in a straight conductor. Now that we can fully define electromagnetic induction, let's not forget that Michael Faraday laid the foundation for what we know today in electromagnetic induction. And he explained this phenomenon using a law. Now, this law is known as the Faraday's law of electromagnetic induction. But I've mentioned at the beginning of the video that there are 2 laws we need to understand if we are going to grasp electromagnetic induction in full. Now, the first one is the Faraday's law. The second law is known as Lenz's law of electromagnetic induction. Now, they help each other to explain what we observe or experience during electromagnetic induction. So let us first look at the Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction states that whenever there is a change in magnetic flux lines or magnetic lines of force, EMF is induced, and the strength of the EMF is proportional to the rate of the flux linked with the circuit. So that you understand this, let's break it down gradually. So whenever you have a magnetic field, it has its own line of force. Now, changing that line of force will cause EMF to be induced in the conductor that causes that change. Okay, so by the time you move a conductor either towards or away from the magnetic field, it causes current to or EMF to be induced in that conductor. Okay, and the strength of that EMF that is induced in the conductor is proportional. That is, that it will increase when the flux linked with the circuit increase, and at the same time it will decrease when the flux decreases. Now, when it comes to magnetic flux, it is denoted with a Greek alphabet known as phi. You simply write an O and then a slash that cuts it into two equal halves like this. This denotes magnetic flux. Okay, and from this Faraday's law, we can say EMF is proportional to change in flux. So since it is changing with respect to time, so we take that using our differential calculus symbols. We say d phi dt, which denotes change in magnetic flux with respect to time. Now, the other part of the law goes on to explain what actually goes on here, the direction of the current. But before we go into that, or direction of the EMF, but before we go into that, let us remove this proportionality symbol and introduce the equality sign. Now, something will happen to this equation. We now have EMF equals. Now, you're going to be having negative N d phi dt. Now, note this. N is number of turns. Remember, we talked about how that you can increase or reduce the EMF induced by either increasing the number of turns in your solenoid or decreasing the number of turns in your solenoid. So the coil matters. How tightly wound the coil is and the number of turns you have in your coil can affect the EMF that is induced. Now, note that this is magnetic flux. Magnetic flux. Now, there is a common confusion here when you're doing the calculation involving this equation, and that is when students mistake this for magnetic flux density. Okay, note that this same magnetic flux is actually magnetic flux density multiplied by area, then of course cos theta, because the angle also matter. Remember that B itself is magnetic flux density. Flux density. A is area of field. Okay, and of course theta is the angle. Now, to complete this, we know that T here is time. So applying all of this helps you to find the EMF that is induced in a conductor by applying the Faraday's law of electromagnetic induction. Now, it's important that I mention this. This negative sign is explained by the Lenz's law. So when we go to Lenz's law, we will explain why this equation has a negative sign from that law. But don't forget that whenever you have a change in magnetic line of force, EMF is induced, and the strength is proportional to the change in flux with respect to time in that circuit, and that is expressed in this equation. The second law that helps us understand electromagnetic induction, as mentioned, is the Lenz's law of electromagnetic induction. And it states that the direction of an induced current, or EMF, is always such that it opposes the change in the magnetic flux that produces it. And just like I mentioned, it is what explains the negative sign that we see in that equation for electromagnetic induction as stated from the Faraday's law. Remember that we say EMF equals negative number of turns, then the phi dt. Remember, this is magnetic flux, right? So this negative sign is telling us that the EMF or the current that is induced is always in such a direction that it is opposing the change in magnetic flux that produces it. I mean, one fun way to always remember this is to think of nature itself as a big fan of homeostasis. Now, what homeostasis means is that when you love remaining in the same conditions, you don't want change in the present condition that you are in. Like, for example, humans maintain their temperature and the pH because of this homeostasis, right? We're able to maintain the same body temperature, the same body pH because of homeostasis. So the same way we can think of nature as such, it loves to remain in the same condition. So whenever there is a change in magnetic flux, now that induced current itself will now create its own magnetic field so that it slows it down, it tries to balance it out. Remember, there's a change in magnetic flux that led to the production of the electric current itself. Now the electric current will now produce its own magnetic field that tries to slow down that rate. And in the same way, if the magnetic flux is dropping, there's a decrease in the magnetic flux. There's also going to be an induced current that will not be in the direction such that it is trying to balance it back, to increase it to where it should be, where the magnetic flux level should be. Remember, the magnetic flux is always fluctuating, increasing, decreasing, leading to induced current. So that current itself will now build its own magnetic field that is trying to balance the system out. And that's how nature keeps all of this in balance. Now, to understand this, let's look at this. Take, for example, you have a cylinder made of copper. Okay, a cylinder like this made of copper. And then I take a strong magnet and then drop it through the cylinder. Do you think it's going to drop fast or it's going to slow down? You see, a good understanding of this Lenz's law will help you know what will happen here. So if you take a copper tube and then you drop stone in there, for example, it drops immediately to the ground with the aid of what? Gravity. Gravity helps it fall to the ground very fast. But when you take a strong magnet, now mind you, copper does not attract magnets. So it means that the magnet itself will not get stuck in the copper tube. It's not going to be attracted to it. But as you drop it through that copper tube, electromagnetic induction starts. And as a result, the field will now begin to balance out. Remember homeostasis, right? It's trying to make sure that the current that is being induced or EMF that is being induced is in such a way that it is opposing the magnetic flux that is producing it. So as a result, the magnet that you drop through this tube will slow down. It doesn't fall immediately through the tube. And this helps you understand Lenz's law. So if you're asked to describe Lenz's law, you can use this as a means of explaining it. But don't forget, in statement, you say that the direction of an induced current or EMF is always in such a way that it opposes the change in the magnetic flux that produces it. Before we go into the applications of electromagnetic induction, believe me, there are several applications to electromagnetic induction. Some of them even lead to devices that you use in your house. But before we can do that, there's a special type of current we need to study. It is called eddy current. Now, when we say eddy current, there are loops of current that are induced within a conductor when you expose it to a changing magnetic flux. Now, what this means is this. Whenever you have a conductor interacting with changing magnetic flux, according to Faraday's law, EMF is going to be induced in that conductor, right? Now, as this EMF is induced, remember that Lenz's law will say that the induced current or EMF is in a direction that opposes the magnetic flux that is producing it. So this opposition leads to the current forming loops, that is a circular swirl within that conductor. You see the current begin to move in a circular swirl in that conductor. Now that circular swirl itself is known as eddies. So that is why it is actually called eddy current, okay, because of that circular swirl you have within the conductor. Now, this eddy current can be of advantage just as much as it is of disadvantage. Now, when you're working with any machines. Talk for example, when you're using the transformer, for example, eddy current can lead to generating intense heat, and this heat leads to waste of energy. Okay, so this is why it is not desirable when dealing with those type of machine. But eddy current can also be desirable, especially when you are dealing with moving coil instruments like the moving coil galvanometer and the likes. In that case, eddy current has a huge advantage. But don't forget that in defining eddy current, you have to explain how that it is a loop of current that is induced within the conductor when it is exposed to magnetic flux. And don't forget, it is advantageous in the sense when you are dealing with instruments that have moving coil, and it has disadvantage in the sense that it generates a lot of heat and can lead to energy wastage. As already mentioned, electromagnetic induction is applied in so many devices. Know that electromagnetic induction itself is when you produce electric current or potential difference or EMF by the time you move a conductor relatively with a changing magnetic field. So that is when you are using motion to generate electricity, then what you are doing there is applying the laws of electromagnetic induction. Now, as I've mentioned, it takes several applications in different devices. Now we'll be looking at these devices one after the other. Look at the main components of the device and the working principle, that is how it applies electromagnetic induction in its activity. So the first one we're going to be looking at is what is known as a dynamo. Now, a dynamo itself is a device that converts mechanical energy into electrical energy, vice versa, meaning that it can also convert electrical energy into mechanical motion. But the aspect we're going to be focusing on is that part where it converts mechanical energy into electrical energy. And a dynamo that does that is known as a generator. Now, you know this as that device that you put on to produce electricity whenever the normal electricity supply you have fails. Now, this can come in different sizes and different form. But for the purpose of this lesson, we're only going to look at generator in two different forms. We have two types of generator. We have the alternating current generator, and then we have the direct current generator. This will be the only two types of generator we'll be talking about. However, take note that this generator can come in different size. Based on what you want to power, the amount of energy you want it to generate, you can have different types of AC generators and DC generators. Some of them are for household works alone. Some of them are attached to larger designs, like the hydropower stations requires generator. The wind turbines also requires a generator. So you see now that generator can come in different sizes. But it's important that you understand the working principle behind each of these generator. That is why we are looking at it in these two types only. So we're going to start by looking at what an AC generator is, that is alternating current generator. We'll look at the major parts it has and how all these parts function together to produce electricity from mechanical motion. The main components of a simple AC generator are listed here. We have the armature, which is a coil, a rectangular coil of wire. We have the magnetic field provided by strong magnets, and sometimes could also be an electromagnet, which is what is used in common day generators. We also have two copper slip rings and then two stationary carbon brushes. Now, the generator itself produces electricity by applying the Faraday's law of electromagnetic induction. Now, the way it's able to do this is when you have the armature itself, which is the ring, the copper that you have winded into a coil. Now, you place this within the magnetic field. Remember, according to Faraday's law, when there is a change in magnetic flux, EMF is induced. So by the time that armature rotates within the magnetic field, it will cause the magnetic flux to change. So as that magnetic flux changes, current is then induced in the coil. Remember, the coil itself is the armature here. So it rotates, leading to current to be induced in the coil. Now that current is going to be transferred to an external circuit by means of the copper slip rings. So that will make sure that the current is transferred to an external circuit. Now it doesn't stop there, the rotation continues, and then that will mean that these two carbon brushes will have to switch the poles. And as the pole switches there, it will go for the second half cycle, and when it does that, current is induced again because it's going to always break the magnetic flux, always causing the magnetic flux to change. That rotation leads to more current to be induced in the armature, that is the coil of the generator, leading to current flowing and then moving to the external circuit that can then be used by the user of that generator. Now, in order to produce this motion, the generator requires mechanical energy to be transferred. Remember that the fundamental law of energy is that it is neither created nor destroyed. It is only transformed from one form into another. This is why you see different types of AC generators. Some of them require that you burn fuel. Now, when you burn the fuel, it will lead to the mechanical motion, that is the rotation of that armature in the magnetic field, and then current being induced in the coil and then can then be used. So you see there, you are converting first from chemical energy to mechanical energy and then to electrical energy. Now there are some that requires the motion from the flowing stream of water, like in hydropower station. You see that the water is damped, and then when it's allowed to flow, it will move a certain wheel known as turbine that then makes sure that that energy is increased to an exponential level, and that is what moves the armature in the generator, and then current is induced in the armature and then taken by the copper slip rings to an external circuit, and just like that you are generating electricity from mechanical motion. And that's the working principle of a simple AC generator. When we do look out for the DC generator in comparison with the AC generator, they are almost alike with just a slight difference. Now, the obvious difference, of course, is that in a DC generator, you are producing direct current electricity, while the AC generator will produce for you alternating current electricity. But both of them rely on electromagnetic induction. So for us to understand why this is possible, let us first look at the main components of a DC generator. Now, this also forms one of the questions you will probably face when asked about applications of electromagnetic induction. Now, the main components of a DC generator are as follows. We have the armature, which is a rectangular coil of conductor. We also have the magnetic field, and then now in the case of an AC generator, at this point here we did mention a slip ring, but here we have what is known as a commutator, also known as split ring. Now this is one of the places where students are easily confused. Slip and split, they are two different things, and it is by the function of these two different things that we generate AC in one and DC in another generator. So please get it right. For a DC generator, you need split ring, while for AC generator, you need slip ring. I will explain how they function in a while. Now, after that, we also need, of course, stationary carbon brushes. Now, mind you, both the AC and DC generator are always attached to a shaft. The shaft is what transfers the mechanical energy to the armature. Thereby, you then convert the mechanical energy into electrical energy. Now, to explain how this all works. Now, the same principle is observed in a DC generator, where once the mechanical energy is transferred to the generator by the shaft, the armature begins to rotate. Now, the rotation of this armature, which is the rectangular coil in the magnetic field, causes it to change the magnetic flux. So as it is breaking the magnetic flux, making it to either increase and decrease, you remember it's changing magnetic flux here, that leads to what? The induced current. So as it begins to change with the magnetic flux, you see that current is induced in the coil. Now, as this current continues to build up, remember in the AC, it is collected by the slip ring to the external circuit. But in this DC generator, as the current is induced, it goes to the split ring, which reverses the polarity or the connection of the coil itself. So making sure that every current that is collected at that point is unidirectional. So you are only going to have current forming in one cycle. Now this is it. Observe, in the case of AC generator, during the first half cycle, you are going to see current generated in the positive side like this. But at the second turn, when the carbon brushes switch, you see that current will be generated in the second half cycle down like this, leading to a sine wave. The current you are seeing there is sine wave. This is for AC current wave. But when you now work with the DC generator, this is what happens. During the first half cycle, as current is induced, you are going to have a pulsing current like this. Then this split ring, the commutator, switches the polarity, meaning that by this time, instead of the current to be formed at this other side, it will still be formed here, but it will be another pulse current. So you see, this is what? Unidirectional. In other words, direct current. Now please get this right. In both cases, the EMF is still alternating, but the current produced in AC is alternating, while the one produced in DC is unidirectional, hence direct current. So this is DC current wave. So this is why you see that in the DC generator, you are producing direct current. It is by the effort of the split ring, which changes the polarity of the armature, the coil itself, thereby allowing the current to be produced in only one direction. Okay, they have their advantages. Of course, many of the devices we use nowadays requires direct current, though we always have to convert from AC to DC by a process known as rectification. However, if you have a DC generator, you don't have to employ the use of an external circuit to do this. You can just generate your direct current and use it with your appliances straight away. But don't forget that you can have generator in two forms: alternating current generator and direct current generator. And as far as how it works, the differences in their components is that for the components of the AC and DC, they are similar. Only one difference in their components. The AC uses a slip ring, while DC generator uses split ring, otherwise known as commutator. And then the wave formed, the currents that they produce, for the AC generator will give you a sine wave, while for the DC generator you have a single pulse unidirectional wave. You have pulsing unidirectional wave. And of course, by their name you already know that the AC generator will produce alternating current electricity, while the DC generator produces the direct current electricity. Don't forget that if you do have any question at all, you can always put it in the comment section and we promise to attend to all of your questions. Another device that applies the principles of electromagnetic induction is the transformer. And no, when I say transformer, I'm not talking about Megatron. Neither am I talking about Bumblebee. I'm actually talking about an electrical device that helps you to either increase or reduce alternating voltages. So this is an electrical device used to increase or reduce voltages. Now, this is why we have two main types of transformers. Now, we have what we call the step-up transformer, so types. We have step-up transformer. And then we have the step-down transformer. And you can identify these two transformers from their basic structures. Now, mind you, they are similar in structure with just slight difference that helps you to understand how to identify a step-up transformer from a step-down transformer. In fact, the way I like to visualize this is that a transformer is just simply a transformer, and the way you orient it just determines whether it's going to function as a step-up transformer or a step-down transformer. And this is true even in practice, because when you look at a transformer and you are able to describe it in full, you see that all you need to do is just turn it around, and then you can change a step-up transformer to become a step-down transformer. Now, what does a transformer consist of? You see, a transformer consists mainly of components of a transformer, Please pay attention to this. The main component of a transformer is it has two coils. That is the primary and secondary. Then it has a soft iron core. And that's it. So what you're going to be seeing in a transformer is, let's take this to be the soft iron core now. Let's take this to be the soft iron core. You're going to see a coil here, and then another coil here. Let's call this the primary coil, and then let's call this the secondary coil. Now, if you look at it here, you see that the windings I have here is less compared to the windings here. Okay? Now, when primary coil has less turns as compared to the secondary turns, it means that what you are having here is a step up. This is step up. Okay? Now, if you draw the same thing, but this time put more turns here and less turns here, you say that's a step down transformer. But take a look at this. If we should flip this image now, such that this now becomes primary and this becomes secondary, what do you have there? A step down transformer. So you see what I mean when I said, to me, I believe a transformer can either serve as a step up or a step down. It's just a matter of the orientation. And this is true in practice, because the primary coil is what brings in your input potential difference or voltage, while the secondary coil is connected to your external circuit, that is your output at this point. Now, when you put in a voltage at this point, it follows the rules of electromagnetic induction through what is known as mutual inductance. We're going to discuss this principle of operation in more detail, but you see here that it's going to transfer this voltage to the next coil. But here is something that has to be done in order for the transformer to function properly. You see, this coil itself, the iron core, has to be laminated in order to reduce, remember eddy current, we talked about it not long ago, the eddy current. In order to reduce eddy current, you have to laminate the core of the transformer. This is to reduce eddy current, okay? Because eddy current will lead to a lot of energy loss due to generation of heat energy. So to reduce that, you laminate the core of the transformer, and then you see that your transformer is able to either increase or reduce the voltage that it is supplied with. Once again, if you're asked what is the basic component of a transformer, know that it consists of two coils, the primary and secondary coil, and then a soft iron core that has to be laminated in order to reduce eddy current. Now let us look at the principle of operation of a simple transformer. When it comes to how a transformer functions, that is the working principle of a transformer, now it depends on mutual inductance. Now the definition is here, but let us first look at how this whole thing comes together, and then we define mutual inductance together. Now look at this. The symbol used for a transformer, the electrical symbol, looks like this. and then we have the soft iron core, and then now let's call this the primary coil, and then this is the secondary coil. Now here's the thing. When you apply a primary EMF, that is the EMF that you apply at the input of your transformer, let's call that E of P, of a specific frequency, when it is applied to the terminals of the primary coil of a transformer, as it begins to move through the coil, it produces an alternating magnetic flux at the core. So this core will have an alternating magnetic flux, which will cause this potential difference to be induced into this secondary coil. Now here's the thing. The EMF E of S that will be induced here, we have the same frequency. They maintain same frequency, but the value of the EMF either increases or decreases based on the number of turns that we have here. Because of the turns, it can cause the EMF to reduce or reduce. Now look at this. This is a typical step down transformer. You can identify this because we see that we have more turns in the primary and less turn in the secondary, which means that the EMF is going to drop in the secondary circuit. Okay, but the frequency remains the same. There's another thing you need to understand here. As the potential difference or EMF is dropping, the current is going to increase. We're going to see all of this by the time we start looking at some of the calculations involved with transformer. But it is able to transfer the EP, which is the EMF at the primary coil, to the secondary coil by what is known as mutual inductance. Now, to define mutual inductance, this is the flow of induced current or voltage in a coil due to an alternating or varying current in a neighboring coil. So we have an alternating current or alternating voltage in this coil here, and then it is induced into this second one by mutual inductance. Now you are able to calculate the EMF in the primary and secondary because they all are connected by a simple ratio. Here it is. You see, the ratio of the EMF in the primary coil to the EMF in the secondary coil relates with the ratio of number of turns in your primary coil and number of turns in your secondary coil. Now if we're going to put it with relations to the current also, we can then say N of P over N of S equals E of P over E of S, which is now equal to the current in the secondary coil over the current in the primary coil. So let's define all of this, where N of P is turns in primary coil, N of S is number of turns in secondary coil, E of P is the EMF of primary coil, E of S is EMF of secondary coil, I of P is the current in primary coil, and I of S is current in secondary coil. Now, take note. For an ideal transformer, the word here, ideal, the power in primary coil must equal the power in secondary. But of course, we know that there is no such thing as an ideal transformer, because transformer faces some energy loss. So it is important to look at those factors that cause energy loss in transformers. We have talked about one of them, which is energy loss due to heat produced by the eddy current. And we mentioned that you can mitigate this or reduce it by laminating the core of the transformer. But there are other things that can cause for energy loss in the transformer. So let us look at these causes of energy loss in transformer that makes the regular transformer not to be 100% efficient, because an ideal transformer is 100% efficient, okay? But there is no such thing. Transformers we have now you can find some in 98% efficiency, 97% efficiency, even more than that, perhaps 99% efficiency, but not 100% efficient. And it's due to some factors that causes energy loss in the transformer. So let us look at those factors that causes energy loss in transformer, and then from there we can then begin to solve problems involving transformers. In the practical transformer, as opposed to an ideal transformer, you cannot have 100% efficiency. And this is due to some sources or factors that causes energy loss in the transformers. So we'll be looking at these factors: the eddy current loss, hysteresis loss, the heat loss, and the leakage of magnetic flux. But not just that, we'll also be looking at how you can rectify these energy losses. So on this half here, we're looking at what causes the energy loss, and on this other half here, we'll look at how to rectify energy loss. Of course, it's in transformers. Now, the first factor that causes energy loss in the transformer is known as the eddy current loss. Now, we've talked about eddy currents before. Now, whenever you are having this sort of magnetic and electrical interaction, when you have a conductor breaking a magnetic flux, there's always production of eddy current. And the eddy current is always opposing the direction of the magnetic flux that produces the current itself. And as a result, it leads to a lot of heat being generated. And as the heat is generated, it reduces the efficiency of the machine, in this case, a transformer. So the transformer is unable to completely move the EMF that is at the primary source to the secondary source. Thereby, what you get at the secondary source is not exactly the power that is put at the primary. So now you see that the power is reduced, so the transformer is no longer efficient. It's not 100% efficient. That's the right word to use there. It is still giving you the potential difference at the secondary. It is still giving you current there, but it does not give you the same power at the primary any longer. So it's not 100% efficient. Now, this is due to the production of eddy current that leads to the generation of heat. It generates a lot of heat and reduces the efficiency. Now, in order to rectify this problem in the transformer, what you do is you laminate the core of the transformer. Laminate the core. So when you laminate the core of a transformer, you are actually reducing the effect of eddy current. So eddy currents are no longer produced as they were, and therefore your transformer is more efficient. The second factor that leads to energy loss in a practical transformer is known as the hysteresis loss. Now, this is energy that is wasted due to the reversing of the magnetization cycle. Now, whenever you put in current at the primary source, because of the alternating voltage there, the core is made to go through a cycle of magnetization. Now, you always have to reverse this magnetization, the cycle of magnetization, on each cycle of the input current. So as a result, this reversing of the magnetization leads to a lot of energy being wasted. Now, the way you can reduce this is by you ensure that you use special alloys for the core. Okay, now if you are not going to be using a special alloy for the core, there's another way that you can reduce the hysteresis loss, and that is by using a soft iron core. Remember that soft iron core are easily magnetized, so as a result you can now reverse the magnetization cycle more efficiently, thereby reducing the effect of hysteresis loss. Another factor that leads to energy losses in practical transformer is what is known as the heat loss or the I2R loss. Now, remember that your transformer consists of coils, and these coils are conductor. Now, every conductor has their own resistance. Okay? Now, because of this resistance, heat is also generated in the coils of the transformer at the primary just as much as it is generated at the secondary coil as well. Okay? Now, due to this resistance, there's a lot of energy wasted in the form of heat. Energy is wasted in the form of heat at the primary coil just as much as it is wasted at the secondary coil. Now, in order to reduce or rectify the effect of this energy loss or heat loss, what you do is you ensure that you use coil with more area. Remember that resistance is inversely proportional to cross-sectional area of a conductor, right? So it means that the bigger the wire, let me put that here, bigger wires. When you use a bigger wire, that is a wire that has more cross-sectional area, you have reduced the resistance of the coil itself, and thereby you have reduced energy loss due to this heat produced in the coil. Another way you can do this, now let me separate this so we don't mix it up. Now another way to reduce this is to use low resistance coil. So either of these two will help you to reduce the effect of heat loss due to resistance of the primary coil. Now don't forget, you can either increase the cross-sectional area of the coil themselves, that is use thicker wires, or you use a low resistance coil to reduce energy loss due to resistance in the coil. And the final factor that we're going to discuss on energy losses in practical transformer is known as the leakage of magnetic flux. Now this is because some of the magnetic flux in the core of the transformer leaks. Now this arises because not all the lines of induction by the current in the primary coil is able to pass through the core of the transformer to the secondary coil, and as a result energy is lost. Now in order to reduce this, you have to use a special type of coil winding. So you don't just wind the coil anyhow. There's a specific pattern or a specific type of coil winding that you have to do in order to reduce this leakage of magnetic flux. Now, to recap what we have done so far, we see here that in an ideal transformer, you ought to have 100% efficiency, meaning that all the power that is given at the primary coil should be transmitted by mutual inductance to the secondary coil. However, due to eddy current, hysteresis loss, I2R loss, that is heat loss, and leakage of magnetic flux, a practical transformer is not 100% efficient. Now, all of these combine together to give you such an enormous amount of energy loss in your transformer. However, you can begin to reduce this effect by following this following process. To reduce eddy current, don't forget, you laminate the core of your transformer. To reduce hysteresis loss, you either use a special alloy for the core of the transformer, or you use soft iron core, which is more of an electromagnet. Okay, and then to reduce the heat loss due to resistance of the coil, you use a coil that has a thick radius, that is a thicker diameter. Use a thicker coil, or you use a low resistance coil. And then to reduce the effect of leakage of magnetic flux, you have to use a special type of core winding. This is how you reduce the effect of these factors that causes energy losses in transformers. So now we know how energy is moved from one coil to the other in a transformer. Remember, that is by what? Mutual inductance. And we know what can cause a transformer not to be 100% efficient. Now let us solve some problems involving the application of transformer just as it applies electromagnetic induction. In order to solve problems involving transformers, there are some basic formulas you need to be conversant with. One of them involves the efficiency of a transformer. But just before we get there, let us recall one of the equations we have already talked about when we're talking about mutual inductance. I remember that we mentioned that the number of turns in the primary coil of a transformer in ratio to the number of turns in the secondary is similar to the EMF in the primary to that of the EMF in the secondary, and then you flip it when you get to current in the secondary to current in the primary. This holds. Okay, but you should also know that efficiency of transformer equals output power over input power. All of this multiplied by 100%. So it is calculated in percentages. Okay, now what is input power and output power? Note that output power is a product of, remember, power according to basic electricity is current times voltage. So when you apply that there, at the output, that's the secondary coil of your transformer, you're supposed to be having IS and ES. While the input power is IP, EP. Now please take note, E can also be denoted with V. So in case you see V, we are still talking about the same thing. Voltage, EMF, they all mean the same in this sense. Okay, so when we put all of this together, it means efficiency is then what? IS, ES over IP, EP times 100%. Now, various questions you are going to be faced with may require you to use this one and then this equation. And some of them may just straight out imply that you use this, just as some may imply that you just use this. If you are looking for the number of turns in either coil of the transformer, this equation works for you. You can either use this side, or you equate these two together. They will always give you number of turns. If you are looking for the EMF at the primary or secondary, you can use this, just as you can use this to also get for current. But when you are solving for efficiency, some question may not give you the input power or the output power or any of these parameters, and you may have to solve them using this relationship here. For example, if you have the number of turns, you can get the input current, output current, just as much as you can get the input EMF and output EMF. And then applying what you get here, you can then solve for the efficiency of the transformer using this particular equation. For you to understand what I mean, let us look at a few questions and apply these equations to them. Don't forget, I'll be giving you tips that will help you understand which of the equations to use. So we understand the question together, we apply the right equation together so that you don't make any mistake when you are faced with question on efficiency of a transformer. If you're ready, let's solve some questions. Let us start with this SSCE question. It says a transformer with 5,500 turns in its primary is used between 240 volt AC supply and 120 volt kettle. Calculate the number of turns in the secondary. Now, there are some things you need to highlight from this question that will help you to solve it without error. So let's look at those important aspects in the question. Now we can see the number of turns in the primary, N of P is given as 5,500. And we know that the number of turns in the secondary is what we are asked to find. So N of S is unknown to us yet. Now, we are told that it is used between a 240 volt supply. The fact that the word supply is used here does not mean that that is the secondary. It means that the transformer is between 240 volts and a kettle. So the kettle is what at the output, while the 240 would be where? At the input. I believe you've got that now. All right. So that means our input EMF, that is primary E, is what? 240 volts. While the E at the secondary is 120 volts. Now let's find the number of turns in the secondary. So we're going to apply the equation NP over NS equals EP over ES equals IS over IP. Now here's the thing. Note that this equation can be flipped anyhow. That is, we can also say NS over NP equals ES over EP equals IP over IS. And you can use any part of this equation. So since we are asked to find number of turns in secondary, I'm going to use this part here to solve it. So number of turns in secondary divided by number of turns in primary, which is 5,500, equals the secondary voltage, which is 120 volts, divided by primary voltage, which is 240 volts. Now, what does this imply? It means that number of turns in secondary equals 5,500 times 120 all divided by 240. So what we have here is 120 here goes once, 120 here goes twice. So we have 5,500 divided by 2. So number of turns in the secondary therefore becomes 2 in 5. That's 2, remainder 1. In 15, that would be 7, remainder 1. In 10, that is 5, no remainders, and in 0, 0. So we have 2,750 turns. And that's the solution to this problem. Here is another question, a grade 12 level question. And it says, a step-down transformer operates a 2,400 volt line and supplies a current of 60 amperes. Now, the ratio of turn of the transformer is 1 to 24. So calculate the secondary voltage, primary current, and power output, assuming an ideal transformer. Now, in order to solve this question, here's what you do. Now, we're going to start by first solving for the secondary voltage. So to get secondary voltage, this is what you have to first understand. Look at this. We are told it is a step-down transformer. So in a step-down transformer, what do we know? The number of turns in the secondary is less than the number of turns in the primary. So it means number of turns in secondary here is the 1, while number of turns in the primary is 24. Now note, this is not the actual number of turns. When they were done in a ratio, it brings you to 1 over 24. So that's why we have these values there. So it still works based on what we are asked to find. And then we are told that the E at the primary is 2,400. Now we want to find E of S. Let's start with this. So we can then say E of S over E of P equals N of S over N of P. Now what does this imply? It means E of S equals number of turns in the secondary, that is 1, times, now E of P, that is 2,400, all divided by, now we have done this, now we're going to have number of turns in the primary, which is 24. So E of S therefore becomes, of course, 24 goes there 1 and it goes there 100 times. And 1 times 100 will give you 100 volts. That's for the first part, the secondary voltage. Now for the second part, we're going to try to find the primary current. So let's call this I. Now for II, we need to find the primary current. So I of P over I of S can now equal E of S over E of P. So let's apply this. Now to apply this, we can now say the primary current equals secondary current times secondary voltage, all divided by primary voltage. Now I of S is given as 60 amps. We're going to multiply that by E of S, which is 100. And then we divide all of this by E of P. Now E of P is given as 2,400. Now let's look at this. 0 cancels 0, 0. It's just like 100 here gives you 24. So we have 60 divided by 24. Now what is that going to give us? It means the primary current is what? Now let's break this down gradually. Now what we can see that can go here easily is 12. 12 goes here twice. 12 will go here 5 times. So we have 5 over 2. And 5 divided by 2 will give you 2.5 amperes. Now we have the primary current. Now the final part says we should find the power output. I. Power output. That is, we are going to be having secondary current multiplied by secondary potential difference. Now the secondary current is 60 amps multiplied by this should be secondary. Okay, E of S. E of S, we have solved that to be 100 volts. And of course, you know the unit of power is watt. So 60 times 100 will give you 6,000 watts. And all of this is assuming that the transformer is 100% efficient. And that's the solution to this problem. Here's another question, and it says a transformer with 50 and 300 tons is used to step down 300 volts AC. Calculate the output voltage. Now this is another SSC question, the senior school certificate exam. So it was adapted from that. So what I want you to do at this point is just pause the video, apply what you have learned so far to try to solve this question. Then you compare what you have gotten with what is gotten at the end of this video. So let us know if you did get the answer correctly, and if there's any other thing you would like us to explain even better, please drop them in the comment section. Now that you've solved it, let us look at what steps are involved in solving this question correctly. Now, when you look at this question, you were not told which is primary and which one is secondary for the number of tons. You were just told 50 and 3,000 tons. But you already know that since the purpose is to step down, it means that the primary tons should be more than the secondary tons. So that means number of tons in primary is the 3,000. And number of tons in the secondary is 50. Now you are told that it has an input of, that is E of primary is 300 volts. Now we want to find E of S, the output voltage. So how do we do that? We say E of S over E of P equals N of S over N of P. Now let's apply this. We can now say E of S equals, now we're going to be having E of P times N of S over N of P. Now what are the values? E of P, 300. Times N of S, 50, all divided by N of P, which is 3,000. Now let's see what happens here. 0, 0, 0, 0, 0, 0. So E of S, here we have 3 times 5, which is 15, divided by 3. And remember, this is in volts. So the output voltage is going to be 5 volts. If this is what you got at the end of your own calculation, thumbs up to you. You have done it right. If you didn't get the same thing, please leave us a question to any part of this calculation that was a bit tricky for you, so that we can help you get even better. This is another SSC level question that says to find the ratio of turns in a transformer which delivers a voltage of 120 volts in the secondary coil from a primary voltage of 60 volts. So you see here that the primary has 60 volts while the secondary has 120 volts. So what type of transformer is this? That's correct. It is a step-up transformer. That's very good. So let's solve the problem. Remember to leave your answer as a ratio. So what we're going to do here is we're going to say the E of S over E of P equals N of S over N of P. Now, what is E of S? E of S, that secondary voltage, is 120 volts divided by E of P, which is 60 volts, all equals the ratio of secondary to primary. So what do we have here? Volts, of course, cancel volts, and what we have is 2. Now, if you divide this, you are going to get 2. But don't forget your answer is supposed to be as a ratio. So you say 2 over 1 is your N of S to N of P. So in your final answer, you have 2:1. This should be how you present your answer, not as a whole number, but as a ratio or as a fraction. So this is the answer to the problem. This is another question that tests your level of knowledge in understanding how a transformer works. Now the question itself says, draw a label diagram representing a transformer which produces 24 volts from 240 volts. Now, you already know that the symbol to represent the transformer looks something like this, okay? And you know one of them is your primary while the other is your secondary. But what this particular diagram aims to achieve is this. The examiner wants to see if you understand the relationship between the primary turns and the secondary turns for a working transformer. So you need to find the ratio of turns for the secondary and primary coils of this transformer. So here's the first thing you do. You know that E of S is 24 volts and E of P is 240 volts. That means we need N of S ratio N of P is what we need to first find. So we'll say E of S over E of P equals N of S over N of P. Now what this implies is that we are having 24 over 240 equals N of S over N of P. And what does this mean? It means N of S over N of P equals 1 over 10. So 1:10. 1:10 could also mean 2 to 20. It could also mean 3 to 30, 5 to 50, and so on. Now, you don't have to draw all this number of turns. All you need to do is, in your diagram, do this. Draw your core and then do this other part. Make sure that this is not as much as what you have here. So now you say number of turns in the primary here. You can call it, say, 20, for example. And say number of turns in secondary is what? Following this ratio, that means you have to have 2 here. Or if you want to write 40 here, then this will be 4. If you want to write 50 here, then this will be what? 5, following this exact ratio. And this is how you draw a label diagram of a transformer. Bonus question: what type of transformer is this? Drop your answer in the comment section. Before we go on to mention other devices that employ electromagnetic induction in their working principle, it is important that we bring a bridge the gap between generators and transformers. Now, we've mentioned in this video that both of them apply electromagnetic induction, and we've seen how they work as we went through the working principle of both the AC and DC generator, and also we looked at the working principle of a basic transformer. And then we went on to solve several questions on transformers. Now, what we're going to do now is to look at how power is transmitted. Now, it's important that I mention this. Every country rely on different means of generating electrical energy. In some countries, they use about 2 to 3 means to generate their electricity. Some rely on just a specific method, but all of them require the use of a generator. Now, I'll be using my country, Nigeria, as a case study so that you can see how energy is generated and transmitted in every other country. They follow similar process, the same physics principle. So let's look at it in stages so that you understand what goes on during power transmission. Now, there are 4 important stages that we're going to be talking about. We're going to be looking at the power plant. Then we look at what goes on for transmission. After that, we're going to look at what happens at sub-power station. And then what happens at the consumer level. Now, before the energy gets to your household, because you are a consumer of electricity, before it does get there, it first has to be generated. And you know what the fundamental law of energy states. Energy is neither created nor destroyed, but it can be transformed from one form into another. Now, like I said, countries depend on different methods. But here in Nigeria, we rely on hydro power generation. We also use the steam, that is heat energy, to generate electricity as well. Now, other means by which you can generate electricity are from solar systems. You can also use wind turbines and the likes. Now, we also use solar systems in Nigeria, but the grid of Nigeria's electricity does not depend on solar electrification. This one is done at consumer level. So as a user of electricity, you can decide to use solar panels for your own household. And then for the wind energy, it's not really in use in Nigeria like that. But there are other countries that do apply that. But no matter which method they are using to generate the energy, what happens there is this. There has to be some mechanical action. So it's either you're using water to drive a turbine. Now that is for hydroelectricity. Now if you are not using that, you can also use thermal energy, that is heat energy, to heat up water and then produce steam. Then you use that rushing steam to drive the turbine. So some call it the steam turbine, but it relies on heat energy. So if you're using that method, that would be thermal energy generation. Okay? Now, aside these two, no matter what you're doing, you see that what is important there is that you're driving a turbine with the motion of either steam or water, and that is mechanical energy in action. Now, what the turbine does is that any little spin will be multiplied exponentially, and that movement is what drives the generator. Now, remember, the armature has to rotate, breaking the magnetic flux in the generator. So as that happens, electricity is induced. We have current being induced in the coil, and then you can begin to transmit this energy. And that's what happened at the power plant level. Now, the energy needs to be transmitted. That is from the power station all the way till it gets to the final consumer. Now, what has to be done here is this. Now, take note. To transfer or transmit power, note that power itself is given as what? IV, current times voltage. So to transmit power, you either transmit at high current, low voltage, or low current, high voltage. But take note, when you transmit at a high current level, what's going to happen there is that because of the amount of electrons moving through the conductor, heat energy is going to be generated in the conductor, leading to what we call heat loss. Heat loss at high current. You can calculate for this heat loss by using the equation I square R. Okay, this is how you calculate heat loss during transmission. So in order to stop this or reduce it or ensure that energy is not lost during transmission, what is done right here in Nigeria is that energy or power itself is transmitted at very high voltage. Very high voltage and extremely low current. Now, this helps us to reduce the effect of heat loss during transmission. So this is why you see that when energy or power is being transmitted in Nigeria, we use very large cables to ensure that resistance is reduced, and at the same time the current at which it is moving is very small. I'm talking about 0.00 something current, where the voltage is as high as 33,000 volts in some cases. Okay, now as it is being transmitted, you can now take this power from the power station. You can transmit it over a long distance when you do it at high voltage and extremely low current. Now from there, it's then taken to a sub power station. Now this sub power station is close to the consumers. Okay, this is where this voltage itself is stepped down a bit because it is very high and you cannot risk transmitting energy at this high level amongst residential area because it can really cause a lot of accidents. Okay, so they have to step it down at this point. And what do they use here? They use a step down transformer. You already know what this step down transformer does. It helps you to reduce the voltage that it gets to that station. Now remember, this is at 33,000 kVA. It gets here and then it is stepped down to about 11,000 kVA, which is slightly safe to be passed through residential areas. Now it is then taken from this sub power station to the consumers. Now how we get to the consumers is that here in Nigeria, virtually every street you get to, you will find some large transformers there. Now that transformer receives the 11,000 kVA power, and when it gets into that, they step it down further. So they use another step down transformer. Now what this does is it takes the 11,000 volts and bring it to as low as 240 volts, which is what is used at the consumer level. Now at this level now, the current must have increased. So sometimes the current gets as high as 15 amperes or at the minimum 13 amperes. So it's between this. Now it gets to this level and then it can be taken to different houses via cables. Okay, so don't forget, the process is what? Power at the power plant, they generate electrical energy from mechanical motion. Then it is transmitted at very high voltage and extremely low current. And don't forget that the purpose of this is to reduce what? Energy loss due to heat. Okay, now after that, it is taken to the sub power station where it is then stepped down to 11,000 kVA, where it can go through residential areas, and then taken to the consumers where they first step it down to the amount of voltage and current that is required to power different households. And then every consumer is connected to this particular power here at this particular rating, 240 volts, and within 15 to 13 amperes of current. And that is how power is transmitted in Nigeria. You can also research to find out how it is done in your own country. I believe some countries use about 110 volts and then even more current, while some use this same amount. So whatever the specification for power in your own country, put it down in the comment section. Now that we've looked at transformers, we look at DC and AC generators, it's important that we also look at other applications of electromagnetic induction. Trust me, when it comes to electromagnetic induction and its application, where you're going to find the majority of questions is from its application in generators and transformers. Now, we've been able to look at that. We looked at the AC generator, the DC generator, and we looked at the transformer. We talked about their working principles and we even solved some problems on its application, right? But beyond that, it is also important that you should be able to list other applications, that is, other devices that apply electromagnetic induction. And that's what we want to do before we end the study on electromagnetic induction. Now, one of those systems that applies electromagnetic induction is the induction coil. Now, what this induction coil does is that it converts low DC to high voltage. Okay, and it is applied in car ignition system. Okay, Now, when you take a look at the car systems, at the ignition system, it is going to be taking about 12 volts of potential difference from the car battery, and it's going to use that to start the car, which requires a higher voltage. And the way it's able to do this is that it works just like your transformer. It has its own coils as well that will then transfer the power from one coil to the other, but raise the voltage. But the difference between this and your regular transformer is that a transformer requires alternating voltage, but the induction coil works with direct voltages. Okay, so it only works with direct current, and it's able to step it up just the same way your step up transformer will do the same. And don't forget that, of course, when you reverse it, it will do the reverse of the action. Okay, it all depends on how it's able to apply electromagnetic induction based on the number of turns in this primary and secondary coil. But don't forget, once again, the difference between an induction coil and a transformer is that this one requires direct current, while a transformer requires alternating current. Okay. Another application is seen in the induction cooker. Now, what this does is it converts electrical energy to heat energy. And it also does this by induction, electromagnetic induction. And it is used in induction stoves, applied in induction stoves. Induction stoves. Now, most of the heaters we have in our houses, the stoves, electric stoves and the likes, apply this principle of induction cooker to be able to convert electrical energy. When it passes it through some coils, it's able to convert it into heat energy. You know that how when you have eddy current in a particular loop, it can generate heat and it leads to energy losses. Okay, but in this case now, you are relying on that and using it to actually cook in your kitchen. So that is another application of electromagnetic induction. Now, we also see it in induction furnace. Now, this is similar to the induction cooker, but with just some slight difference. So it also converts electrical energy to heat energy. Okay, and it is applied to melt metals. Like when you go to your major jewelers, what they do is they use the induction furnace to heat up gold, silver and other metals like that and shape them into jewelries, whether it be earpieces or neck pieces and the likes like that. They are able to melt gold, melt silver and other metals and fashion them into nice fashion statements that you use in your bracelets, your necklaces, your earrings and the likes. Okay, and they apply induction furnace, which relies on electromagnetic induction. And then finally, the most common one here is the induction motor. And what this does is it converts electrical energy to mechanical energy. I like to think of it as the reverse of a generator, because a generator will convert mechanical energy into electrical energy, while the induction motor will convert electrical energy into mechanical energy, and it relies on electromagnetic induction. And it is applied in a lot of devices, so like your electric fans, your washing machine, pumps, electric pumps, and so many other devices like this that requires the induction motor. Remember, what it does is what? Convert electrical energy into mechanical energy. And these are the applications of electromagnetic induction. Don't forget, you could be asked to list and explain working principles. Now, when it comes to working principles, most times you'll be asked for the generator and then for the transformer. But when you're just asked to list, it's just important that you're able to mention all of this Please drop in the comment section other devices around you that apply electromagnetic induction, and let's discuss about them. Now let us look at some questions on electromagnetic induction. Now don't forget that as you solve these questions, I'll be giving you tips where you can always recognize how to identify the correct answers, or how to understand what the examiner requires of you when you see questions like this. And all of this depend on what we have learned so far on electromagnetic induction. So even beyond this, you still have to put in some practice and try other questions yourself. But don't forget that there are some things you just have to look out for, and you get them as we solve the following questions. Now, the first one we are looking at is a JAM question from 1999. Now, this question says, the core of an efficient transformer should consist of laminated pieces of metal in order to... Now, before we go on to look at the options at all, you have to understand the concept that this question is built on. Now, we know that there's no such thing as an ideal transformer because there are so many ways by which energy can be lost in a transformer. And we did talk about 4 though. We looked at energy loss due to eddy current. We looked at hysteresis loss. We saw energy due to heat loss. And we saw the one due to leakage of magnetic flux. Those 4 items, do not forget them because you can find even theoretical questions. I think there are some questions you see in past questions that talks about identifying how energy can be lost in a transformer, or where they talk about what are the factors that make a practical transformer not to have 100% efficiency. Okay, so but in this particular one, we are looking at the one that is due to eddy current loss, because it says that you have to laminate the piece of metal, laminated piece of metal in the core. And when you laminate the core, what you are doing there is you are reducing the production of eddy current. Now, you know eddy current itself produces heat, which leads to energy loss in the transformer, right? So this focuses on eddy current. So you want to reduce eddy current and reduce heat energy. So let us see which of the options provided is the correct one. Now, A says increase the heat produced by increasing eddy current. Now, when you increase eddy current, you are actually increasing the heat, but you are making the transformer less efficient, not more efficient. B says increase the heat by reducing eddy current. If you are reducing eddy current, there's no way you are increasing heat, except you are looking at the wires that make up the coil. You can actually increase heat in that by actually making it a more resistant wire, or you use coils that has very small diameter. Maybe that way you can also increase heat as the current flows through it, but this does not make the transformer efficient as well. Now, option C says reduce the heat by increasing eddy current. Now, these two do not even go together at all, as when you increase eddy current, you are increasing the heat produced in the transformer and reducing its efficiency. So it's a complete no-no. So leaving us with the final option, option D. But let's check and see if it is correct. Now, this says reduce the heat produced by reducing the eddy current. Now, that is the correct statement there, because when you laminate the core of your transformer, then you are reducing the production of eddy current and also reducing the production of heat, and therefore making the transformer to be more efficient. So the correct option is D. Here is another question from the 2008 JAM. The question says the DC generator has essentially the same component as the AC generator except the presence of... Now, this is a very obvious one, so I'll allow you to go ahead and pick your option. Okay, so in this question here, we see that both the DC generator and the AC generator have the same component except for one thing, and we've always been mentioning this along the study when we're talking about the generator. Now, remember that both generators have carbon brushes, a pair of carbon brushes. Both generators have the armature, which is your rectangular coil or loop. Okay, but now where they are set apart is in the presence of slip rings and split ring. But this is where it gets tricky. You need to understand which one you are trying to identify. Is it for the DC or the AC generator? It's about how the question itself is set. So we are looking at what the DC generator has that the AC generator does not have. Okay, you see that now. So it's the component that is peculiar to DC generator we are supposed to highlight, not the one to the AC generator. So the answer is not slip ring, but rather split ring. Remember, another name for this is commutator. Okay, but because they look similar, this is where examiners usually bait students to make them think perhaps it's either of these two because they look alike. But don't get confused. The correct answer here is split ring, which is option C. Here's another question. Now, this time we are told that a step-down transformer has a power output of 50 watts and efficiency of 80%. Now, if the main supply voltage is 200 volts, calculate the primary current of the transformer. Now, I have left the options in these questions out. It is also a UTME based question, but because it appeals to both UTME preparation and WAEC as well as NECO preparation, I have left out the options so that you see the entire process that leads to picking the correct answer and not be limited by just options. So let's look at how it is solved. Now, in this case, we are told that the efficiency is 80%. So we're going to use the efficiency of a transformer, which is power output divided by power input. So we already have the power output as well as the efficiency. The efficiency is 80%. That means we have 80 divided by 100 equals, now the power output is given as 50 watts. So we divide that by, now the power input is supposed to be E of P times I of P. So we are asked to find I of P. So we put that I of P multiplied by E of P, which is given as 200. Okay, now from here we cross multiply. So we're going to be having 80 multiplied by 200 I of P equals, now to this side we have 50 multiplied by 100. Now this is going to give us 16,000 I of P equals 5,000. Now dividing both sides by 16,000, that will mean we have I of P equals, of course, this 1,000 parts cancels out the 1,000 parts here. So we are left with 5 divided by 16. And 5 divided by 16 will give us 0.3125. Now this is in amperes. Now from this point, you can now approximate the value of the current to 2 decimal places if you like. Now, except the question itself asks that you specifies the number of decimal places you work with. So in this case, we're going to say the current in the primary coil is approximately 0.31 amperes. And that's the solution to this problem. This UTME question from 2012 says, the Fleming's right-hand rule, in the Fleming's right-hand rule, the thumb, the forefinger, and the middle finger, if held mutually at right angles, represent respectively the, now we have a number of options. We have 4 here. We see motion, the field, and induced current. Induced current, the motion, and the field. Field, the induced current, and the motion. Induced current, the field, and the motion. Now, let's recall the Fleming's right-hand rule. Once again, I'm saying this based on how this video is filmed. What you're seeing is a mirror image, okay? So what I'm raising now is my right hand, but it may appear to you as the left. So understand with me. Now, you hold out your own right hand just like I'm doing, okay? Ensure that your thumb is pointing upwards, your forefinger or index finger is pointing forward, while the middle finger is pointing sideways like this. You see now that they are held mutually at right angles, 90 degrees to each other, okay? Now, this is how we describe the direction of the motion, the field, and the induced current using the Fleming's right-hand rule. And you recall that the statement says that if you are stating Fleming's right-hand rule, you say if the thumb, the forefinger, and the middle finger of the right hand are held mutually at right angle, such that the forefinger is in the direction of the field, then the thumb will be in the direction of the motion, and the middle finger will be in the direction of the induced current. But here now it has arranged it as thumb first, then forefinger, then middle finger. So thumb represents what? The motion. Forefinger or index finger represents the field, the magnetic field, while middle finger represents induced current. So motion, field, induced current. Again, motion, field, induced current. Now you've got it. So let's pick our answer. Motion, the field, and induced current. So that is option A. Here is another question on transformers. Now I would like to urge you to please try to solve this question yourself first. Then compare your solution to what is done in this video, just to gauge how well you know how to solve problem on transformers. It is important to us to get a response from you as well, so that we see if you've truly gotten the concepts behind electromagnetic induction as it is applied in transformers, and also in case if you have any challenge, so that we can be able to profile solutions or make other videos that will help you improve on them. So please solve it yourself first, and you can pause the video now and try to solve it yourself. And then if you do get it right, mention it in the comments. Let us know that you got it correctly. And if you didn't get it correctly, we'd like to know where it went wrong, the part of the solution that yours went wrong at, so that we can assist you to get better with such kind of calculations. Now that you solved it, now let us solve it from this end. So observe every step so that you'll be able to identify if you miss any of the steps and see how we can help you to improve on such steps. Now the first thing that you should do that will help you solve this kind of problem without error is to identify what you are given. Now we see that in this case we have a transformer that has 300 tons of wire in the primary, so that this number of tons in the primary is 300. Okay, and 30 tons in the secondary, so number of tons in secondary is 30. Good. Now we are told that the input voltage is 100, so that is E subscript P. That's input voltage. That is 100 volts. And we are asked to calculate the output voltage, so that is E subscript S. That's our unknown. So to solve it, we are supposed to apply E of S divided by E of P equals N of S divided by N of P. Now, here what do? We impute. So E of S divided by E of P is 100 volts equals number of turns in secondary, that's 30 divided by 300. So from here you can now say E of S equals 100 volts times 30 divided by 300, which would give you, now here you have 3000 volts divided by 300. And when you divide this, of course, 0, 0, 0, 0, so we have 30 divided by 3. So the voltage in the secondary coil is going to be 10 volts. And that's the solution to the problem. Now please don't forget, if you did get the same amount of voltage in the secondary coil, that is 10 volts, ensure that you put that in the comment section so that we know that you got it right. Now, if you didn't get the same 10 volts, that means you must have missed a step or gone wrong somewhere. So please look at this once again and identify where your calculations went wrong, and let us know in the comment section so that we can help you improve on that. Now, with that being said, we've come to the end of our study of electromagnetic induction. I believe it has been an interesting ride, as we've been able to see how this principle, something that was first observed by Michael Faraday, has gone on to improve over the years and is now making our own lives better. Okay, we've seen several of its applications, and you also use it even though you never knew before now, and some of you did know, however, but we see the applications in our day-to-day life, and it is interesting to always watch. Now don't forget that we are trying to reach many more students like you who do not have access to this kind of videos that we produce right here on Oya Learn, your flawless school too. So you can help us to achieve this by ensuring that you share the video. All you need to do is click the share button. It doesn't cost you any money. All you need to do is click the share button and help us widen our range to help more students get even better. And if you're watching the video and you have still not subscribed, come on, just take a second of your time, click the subscribe button. And trust me, one other thing that can assist you is to ensure that you click the notification bell icon, because you don't want to miss any of the amazing content coming right here on Oya Learn, your flawless school tool. So please ensure that you click your notification bell icon because YouTube will always notify you every time we put out a new content once you do that. Thank you so much for following the video so far. This brings us to the end of what is planned for the first term of SS3 in physics. Be rest assured that we have many more amazing content right here on Oya Learn. So stay tuned with us as we continue to make your academic journey even better. Thank you. Bye for now.